Okay, so last video, ouch, in a wheelie chair and also, okay. Last video, I went over how this vertex attribute works and how it points into a buffer. This video, I'm going to answer a question that a lot of people have quite quickly, and a lot of people don't, it's not always intuitive what the answer is. So that question is, what if we want our vertices to not even that, what if we want our triangle to just, not always be orange? Like we've told this is, we set this as orange by f color equals this. I mean, we can change this, to be, I can put it back to red, but what if I want two triangles and one of them is, not red? Or what if I want the user to pick something here without having to reload the web page or something like that? Well, with enough talking, with all the talking I've been doing about pipelines, I hope that it may be, maybe not obvious how to do it in here, but, maybe I'll go over it here. The answer to that is, we've got our, we've got our vertex shader and our fragment shader, and the fragment shader spits out some color. Right now it's always spitting out orange. What we want to do is to basically make another vertex attribute called a color, and that'll point somewhere. We'll get to that. That'll be number 2 if the graphics card is nice to us. Maybe it'll be number 6, but whatever. We make another vertex attribute to feed into here as data into our vertex shader, and then the vertex shader is going to spit out the same GL position. But then, again, because it's a pipeline, it might also spit out some vertex color, V color. Now the fragment shader is able to, instead of always spitting out orange, it's able to, if it wants to, do some, do some math and spit out some fragment color, F color, that is derived from V color. Or in some cases, you might get just like you can have arbitrary number of inputs, you can have arbitrary number of things coming between stages of the pipeline. So that's the approach that we need to take. Another set of inputs and another set of inputs and some outputs from the vertex shader and inputs into the fragment shader. So before I jump into code, we'll go over. Obviously, we need to have them somewhere. So let's make. Keep moving this board. Maybe I should lock the wheels. Like I mentioned in the first video, I'm wigging the hell out of these videos. There we go. All right, so now instead of having XY, 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 what we want is for our new buffer to hold in it. What we're going to do instead is X, Y. I'll have to bear with me. X, Y, RGB. X, Y, RGB. That's way too close together, but whatever. X, Y, RGB. And so that's what we're going to start with. So just like before, we call create buffer, bind buffer, and buffer data, and that will put us off. I guess I shouldn't have erased that green part. That'll put us off back in the same spot we were before, where we have some buffer. Oh my goodness. I'm deteriorating here. Wow. Fancy line. There we go. Put us back into this state. We've got our XY RGB, our XY RGB, all bound together. Whoa. Now, the problem with this, or the problem that we'll run into, is that we have to put a little bit more thought into our vertex attribute pointers here. So I think once it's drawn out like this, it's pretty obvious what we have to do. Hopefully, if we start thinking about these arrows here. So A position, once again, is XY. That's our A position for every vertex. We kind of have that's a vertex, and that's a vertex, right? We've got 3 of them, and each one, and that's just because that's the way we've decided to organize our buffer, is like this. We could have XY, 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 RGB, 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 whatever. Again, hopefully once I start drawing these, maybe I need to move this back. Hopefully once I start drawing these arrows, it'll make a little more sense again. So you need to tell the graphics card that A position, to find any given A position, start at offset what? Where does my XY start? Well,
0.
Yes, exactly, 0. So A position is, I'll write like a little comma separated thing here. A position is offset 0. And so that means it goes up here. So that's great. Graphics card now knows how to find A position. However, I mentioned last video, which was like 20 minutes ago, that when we said offset 0, stride 0, the graphics card was just kind of figuring out how far to jump ahead to find any given attribute. But now, if we say that A position is offset 0 and it's 2 floats, then what it'll do is it says, okay, that is A position. Then it'll try and read the next one. And it'll get this, RG. And it'll try and read the next one. And it'll get BX. So that's definitely not what we want. And you'd be amazed at how, this one little, we're missing one number from our function call, but it really messes up what our triangles look like, because now we're trying to read some color data as position data, and it's wildly wrong. And you can end up with some spiky triangles because points move to the, if you have a, RGB, you end up with some values that are exactly 1 sometimes. And so you might end up with points that are way up in the corner. So what we have to do is to say that not only do we have position 0 and 2 floats, we also have to tell it how far to jump to get to the next XY. That's what stride is. Stride is the distance from this X to that X, right there. So you can see our 3 things here. Those are the 3 numbers we passed. GL float and false are the what data type is it and do I normalize it. But the other 3 numbers are these. So we've got our offset is 0, and then we've got our, maybe I should be using different colors, but whatever. Our offset is 0, it's 2 floats, and what's our stride? It might be tempting to say 1, 2, 3, 4, 5, 6, but don't forget that we are 0-based indices, so it's not 6, it's 5. And also that the offset and stride are actually specified in bytes, which, because these are each 32-bit floating point numbers, they're 4 bytes each, which is 5 times 4 is 20. So 20 bytes. So that is the full amount of data that this pointer has to hold. You can think of it like a fat pointer if you do systems programming. So that's our, that's how we do that. So the next question then is A color. Again, it's hopefully, now that I've done this drawing, I hope it kind of makes sense intuitively what should happen next. A color needs to point. I've kind of screwed myself with all these things written everywhere. Maybe I will use a different color for this one. A color needs to point here at this R. It needs to be 3 floats wide, and its stride needs to be, again, to the next R, which you'll notice is again 1, 2, 3, 4, 5, is again 20. So this time what we have is an offset of 0, 1, 2, which again is in bytes, not in numbers. So what we want to pass is that our A color is going to be 8 bytes, 3 floats, I'm writing sideways here, 3 floats, with a 20 byte stride, again writing sideways. 8 bytes offset from the start, read 3 floats, and then skip 20 bytes to get to the next one. And by specify, it feels very weird to specify pointers like this, but again, it allows the graphics card to find any nth, any ith vertex attribute by saying, okay, I want a color number 812. It starts at 8 and adds 20 times 812 and then reads 3 floats. And then it can run that vertex shader. So I think to complete this video, I will quickly, I think I should have time to, I'll do this in WebGL right after I have a sip of water. All right. Boop. So let's do that. So step 1 was I needed to add another vertex attribute, which I do just by defining a new one up here. I want a vec3, and then it's going to be called a color. And then I need to define an output to my, I think I erased it, but I need to define the arrow from my vertex shader into my fragment shader. And that'll be an output of vec3, and we'll call it vcolor. And then this one needs to have an input vec3, also called vcolor. And they have to be named the same to get them to kind of tie together like that. And then what I'll do is I'll just say, okay, whatever I got from the vertex shader, I will use the 3 components of that with full opacity and do that. And you can see right away it goes black. And that's because, well, I haven't given it any data, and so it defaults to just 3 zeros. Last thing I need to do is, as silly as it is, this is my input to the vertex shader. Output from the vertex shader, I need to do vcolor equals a color. No, yes, that way. Yes, those are both vec3s, yeah. So next, I want to add my x, y, r, g, b. So I'll just pick some arbitrary colors. Let's do like 1.0. We'll do 1.0, 0.0, 0.0, and then 4.000. R, G, and B. Those are some good colors. And what you'll see as soon as I hit save here is that everything gets all screwy. And that's what I said would happen, right? Because what I've done now is I'm doing the thing where I'm reading x, y as position data, as a position. I told it would be 2 floats. And then I'm reading RG as 2 floats. Because all I said was that, all I've told the graphics card right now is that a position is at 0 and it's 2 floats big. So what I'm going to do now is I need to correct that by coming in here and saying that a position, it is still 2 floats, and I'm not going to normalize it. But now its stride is 20 bytes. And I'm actually going to do that by, const. I'm going to do a thing up here where I'm going to define some, I don't know, like float 32 size equals 4, just so that I don't have random unlabeled numbers in my code. So now it's, each one has a stride of 5 floats apart. And there you go. Our triangle is back because now it is starting here, reading 2 floats, and then skipping by 20 bytes, or 5 times 4, which I put in my code. Next up, I just need to tell a color. Grab a color from my little thing. So same way as I did before, const a color, get attrib location from the program called a color, gl.vertex attrib pointer on a color. This one is 3 floats. It is not normalized. False. It is also 5 floats apart, but its offset is 2 floats in. And darn it, and I also have to enable vertex attrib array, a color. Ta-da! There we go, nice and rainbow. You can see just how simple that was. Again, hopefully with my little diagrams, it kind of makes sense what's happening. This vertex, we told the graphics card that the data required to draw this point on the screen is some position and some color. And then we told it that, when it's done drawing this vertex, what it'll get out is a position and some color to spit into the next stage. And that stage takes that color and just spits it out as a fragment. And this is a good opportunity to show that obviously there's a vertex here and a vertex here and a vertex here. But there's a bunch of colors happening in the middle here that I defined these 3 colors, but we're getting purple here. And that's because whenever you have outputs from the vertex shader, there's fragments, pixels basically. Some other graphics libraries actually call this a pixel shader, not the fragment shader. I think DirectX does that, maybe? I don't remember. But you can see that it basically interpolates, it gradients smoothly. And it'll do that like for any, not just colors. Like you might give the fragment shader like a direction vector for each corner. And then it would kind of like, for this point, it would be halfway between this one's direction and that one's direction. So this is just a good showcase of things interpolating smoothly. Yeah, there we go. I think that's a good good example of controlling, data with that. How long am I on recording here? Let's see. 16 minutes. All right, we'll get to next video cliffhanger. We'll get to rendering more than one triangle.